Okay, the shank of the tool, it's this part here, is the next thing I'm going to make, but the plan states to machine this from a solid piece of steel, and the kit supplies a piece of mild steel for this, free cutting mild steel, but I don't like that. I want the shank to be somewhat hardened, so it's more resistant to wear and shop use. So I'm going to use a 10mm dowel pin and glue on a piece of mild steel as the flange. And as you can see, I already found two dowel pins, 10mm in diameter and the same length. And I prepared two pieces of free cutting mild steel, turned down in diameter and drilled and reamed to a very snug fit on the dowel pins. We will take some Loctite 648 retaining compound and stick them together. I will do that in a vise so I can press them together after I applied the Loctite. I always like to apply the Loctite to the leading edge of the bore, and it spreads itself out when the part gets pushed in. There we go. Get our calipers ready. There we are. Okay, we have both of the shanks done, and the two-part construction allows for a hardened shank, 10mm in diameter, and a soft end that can be machined on the lathe. I could have roughed them out of a drill rod, harden and grind them between centers, but that's too much of a hassle for that part. Because the end of the shank does not need to be hardened. Okay, you saw me just finish the two shanks for the rotary broaches, drilling the mounting holes for the broach itself and machining the key that aligns the broach to it. So we have those two parts done too. We have the spindle with the bearing package. The only thing that's left, apart from the cutting tool itself, is the housing. And I decided to use the free cutting mild steel that is supplied with the kit to machine it, because there is no real wear on it. The spindle is subject to wear because you insert the tool, and the tool exerts force on the spindle, but the contact points between the bearings and the housing are so big that there is no real wear on the housing, and mild steel should be way good enough to handle that, and it machines super nice, so we're going to use that. And yeah, that's the spindle with all the bearings on it. This will slide right into it, and the retainer nut will screw in from the front and hold this whole mess together. Okay, the next part we're going to make is the housing. I already did the first one, and as you can see it needs a series of condo bores and a 0.5 by 20 by 0.5 millimeter fine thread for the land nut that holds everything together. And as you can see, this one is already done, machined completely from one side and then parted off. When I have the second one this far, we will take both and finish the rear side, and also there has to be some milling be done on it to finish them. All in all, this is the most complicated part, most steps involved. The spindle is also not that simple because it has rather close tolerances, which has this too. But it's a good exercise for a beginner in boring. So let's take a second piece of stock, clamp it with about 40 millimeters of hangover. Okay, now we take a CCMT 06 boring bar and machine all the counter bores. And we will use the carriage stop to get our depth. And as I don't have a good way to measure such small diameter holes, I threaded all the bearings onto a screw, and so I can use them as a plug gauge. When I get up close to the diameter, I can check my diameter with those. This is the smallest, the rear diameter, and this is the big one. So let's go. While I can measure the diameter in front here, I cannot check the diameter 25 millimeters deep in the hole. So I would need either gauge pins or a tri-mic, a 3-point internal mic. But I don't have either one because the tri-mic costs about €1,000,000 and the plug gauges are, yeah, gauge pins just are expensive because you need a hell lot of them. At work we have a 1/100th of a millimeter stepped set of gauge pins from 1 to 10 millimeters, and that takes a whole small lister cabinet of space. But it's convenient if you have them. Okay, that starts to be a very good fit. Almost a bit very tight. I will take a spring pass. Okay, this is the diameter for the axial bearing, and this needs to be a light sliding fit, and that's what we have here. Because the axial bearing, of course, doesn't carry any radial load, so it can have a rather loose fit. I think this is 2/100th of a millimeter oversize. just for fun, we can measure it. Yeah, as I said, 200 millimeter bigger than nominal. So that's a very nice, sliding fit. Now we need to bore the front bearing, the diameter for the front bearing, the main radial bearing. Okay, part is still warm, so the fit will get yeah, a little bit tighter, so that seems to be okay. So now we turn our thread relief, already using a threading boring bar, and our major diameter for the thread. The plan calls for 2 mm of thread relief, and that's plenty enough for a 0.5 mm pitch thread because the carriage is moving so slow when threading such a fine thread. And also I changed the settings on the VFD on my lathe finally after 5 years, so it stops instantaneous like this. Before that I had about 5 seconds of ramp until it stopped, and that's annoying when you thread. Now we turn down the internal diameter to 19.5 millimeters. That's the hole size for a 20 by 05 millimeter thread. Okay, we should be very close to our final threading diameter, so we can test it with the gland nut. And I found a spanner, face spanner in my collection that fits the nut. And that's threading in, but it is a bit tight, so we'll give it another 2 or 3 hundredths of a millimeter. So it goes in nice and smooth. Okay, there we go. That's our... Yep, we just bottomed out. That's good. That's a very nice fit. You can open the lead nut of the carriage and disengage the drivetrain for threading because it's just noisy running at higher speeds. And we try to get this nut out. The gland nut is too thick. I parted them off and left about 1 millimeter on the thickness. So while we have the body of the broaching tool in the chuck of the machine, we can face it down. And for that we take the bearing, drop it in the seat. If we can get it in. Ooh. That's a tight fit. And screw the bearing down with the gland nut. That way we can face it to the correct thickness. Just machining it down until it's flush with the body of the tool itself. There we go. And deburring the screw hole in the nut. Okay, now we can part it off. That's the body of the rotary broach finished from one side. Rear side has to be done still. Okay, the plan calls for two parallel flats on the body of the rotor broach, and what machine is better to produce parallel surfaces than the surface grinder? Of course, a round part doesn't stick on a magnet very good. As you can see, can easily move side to side. It holds it reasonably well down, but side to side is there is no restriction. So what you have to do when you want to clamp something round on the magnet chuck, you have to block it in. In this case I'm using some blocks and some bigger parallels. And one parallel behind it, so nothing can move. And now we're removing 0.5 millimeters of material from this side. Then we flip the parts around on the freshly ground flat, and then we're removing another 0.5 millimeters. Of course you can do this with the milling machine, it would not be a problem at all, but I find the surface grinder more convenient in that case. Now, as we have a flat spot on the parts, the holding force of the chuck is already way bigger than before, but I'm still blocking them in from all sides to prevent any catastrophic mishap. Okay, we need to machine the rear end of the body to an angle of 1 degree, and I figured I'm using a toolmaker's vise clamped in my big vise set at 1 degree, and I'm using my small sine bar to get the tilt of 1 degree. I already did the math, and we need 0.87 millimeters on one side to get 1 degree. Of course I don't have a 0.87 millimeter gauge block, but I have a 1.8 and a 1.07. That results in a gauge block stack of 2.87. That means that we have to place a block with 2 millimeters on the other side to get a difference of 0.87 millimeters. Sounds horribly complicated, but makes totally sense if you're okay. That's the gauge blocks, that's the sine bar. We can move the sine bar back to the rear side of the rear face of the vise and use one of my toolmaker's magnets to hold this whole mess in place so it doesn't fly all over when you knock it to the right angle. And the magnet is really nice for this purpose because it holds the sine bar in place and aligns it with the vise. Okay, we get, let's zero it out, 0 over the whole distance, and that's way more than precise enough. The manual of the rotor broach calls they just place 0.45 millimeters of feeler gauge on the one side of the part to tilt it at 1 degree, which is the sine principle too, just a little bit cruder. But as I have all this stuff here in the shop, of course I'm using the sine bar. Okay, now we have to remove material until the whole surface is at 1 degree angle to the axis of the broach body. And to get the depth, we want the plane to intersect with this side of the housing. So I will step down with the end mill until there is just a faint blue line left. Now we can cut the 4mm slot, and I messed up on that part because in the plan the slot is in the shank and the body of the broach gets the key. I did it the other way around. Shouldn't make difference, I hope. Okay, and that's the fit to the shank. I can feel that it tips over slightly, and that's because up here we have a sharp corner, and this part also has a sharp corner, and those intersect, and I have to bevel everything slightly, and then we will get a nice tight fit without rocking. But that's a good fit. Now we need to drill the tapped holes, 3mm thread, so we can mount those two guys together. Okay, power tapping the 3mm thread at 95 RPM. I stopped 0.5mm before the tap bottomed out and turned the tap by hand with the gear of the machine disengaged down until it hit the bottom of the hole. That's the nice thing about the depth stop with the dial indicator. I can exactly see what's happening. Okay, now I hit my dead bottom of the hole, and now I can unwind the tap. Okay, I think that's enough for this episode, but I have a short teaser for you. As you can see, I already have kind of finished one of the rotary broaches, and we're going to cut a 4mm hex in some free cutting mild steel. And there we go. That's a nice, clean 4mm hex. Only the entry is a bit jolted up because I didn't feed hard enough on the beginning, and then the tool seems to skip over the material. So I would have to re-chamfer the edge now to clean it up. But you can see that I get quite a nice hex with nice walls, clean walls, and a 4mm Allen wrench fits super nice into it. So I think this project is going to be a success. Thank you all for watching. Thank you for Heminway Kits for this awesome kit. The drawings supplied with this kit and the instructions are top notch, and thank you to Kirk from Heminway Kits allowing me to show parts of the plan on video. So if you want to build this rotary Broach, please go out to Heminway Kits and buy the set of drawings with the kit. It's worth it. In the next episode we will do the finishing touches and make a set of brooches, hex and maybe square, but I'm interested mainly in hex brooches because I can make specialized screws that way. So see you next time.